You're live now.
Okay, I'm live now.
So I'll just introduce you. Hi, everyone. So we have our next talk, and this is a talk by Jitin, and he's going to be
Wait, wait,
talking
wait,
about
wait, wait, wait.
interface portable instrument for science experiments. Um, Again, this is going to be looking forward to an excellent talk from Jitin. You're live, Jitin.
Okay. Hi, everyone. I'm going to talk about how we can use Python to create graphical interfaces for hardware that connects to your laptop via the USB port. And as a case study, I'm going to use a device called XSpice, which is this is the latest in a series of devices that have come out from the XSpice project. So what this is essentially is that it's a multi-purpose data acquisition hardware. It has a microcontroller sitting inside, which can run, which can accept commands from your USB port. And there's a software and a Python library running on your laptop, which gets data from this. And Python is very good at visualizing data and analyzing data, etc. So you have a complete instrument that goes with your laptop. So this is a brief overview of what it is. You have the hardware, which can interface with your real world. It can interact with sensors. It can measure voltages. It can act as an oscilloscope, etc. And on the Python side, you have a Python library, as well as you have plots and you have controls for acquiring various data. Okay, so as an example, you have C code running on the hardware, which looks maybe something like this for measuring frequency. Frequency as in the time intervals between digital signals. And on the Python side of things, you have a corresponding command that will, a corresponding function call that will ask the hardware, okay, measure frequency and send back the data. So what are the key modules and tools that were used here? So one is PySerial, which is of course for communicating with the hardware. Second is that is a struct library, which basically packs data into binary forms and unpacks it for more usable forms in Python. Then you have the graphical interface, which was made with PyQt. And you have all plots made with PyQt-Graph. And you have NumPy and SciPy for analysis. Then there's documentation, which is done with Python Sphinx. It's easy to translate into various forms. And then, of course, there is packaging. So, in order to make this a complete unit and ship it to end users who may not be developers, you need to package it into friendly forms. So for example, on Windows, PyInstaller is very convenient. It makes one entire bundle, which includes the Python interpreter, all modules, etc. And there's also PyPy, which is also something we've used in this project. Okay, so starting off, this is the interface for the oscilloscope. So let me just show you a brief demo here. I'll switch to the code and show you the hardware here. I hope you can see the hardware. I'm not sure if it's clearly visible here. Can I get some feedback from backstage?
Can you hold it up a little bit closer to the webcam? I mean, the inclination.
Okay, so I can show you another unit right here.
That's a little better.
It's clear now, right?
A little back. Yeah, okay. So those are, I can just see the pins and stuff. Yes.
Okay, that's good enough. So what I'm trying to show here is that you have the hardware connected to your laptop via USB port. And here I have a Python script, an entire Python package, which is now acquiring data from the hardware. So right now what you see is an oscilloscope with no signal input. If, for example, I take a signal such as the waveform generator here, I plug in a wire and I connect it to the oscilloscope input here. And second, just disconnect. Yeah, so you see a sinusoidal signal here, right? Which is actual real data. It's coming out from a waveform generator, which is one part of this instrument, going into the other. And you can do things like vary the frequency of the waveform generator and such. And just to be sure that it is a real signal, I'm going to connect a piezo buzzer here. So this is actually a speaker. It's a buzzer which resonates. Its maximum resonance is around 3000 hertz. So I'll just plug it into this waveform generator, set it to around 3000. So you can hear a high-pitched shrill noise here, right? Okay, so
yes,
let me come back to the part where we make the UI first. So in order to make the UI, we use something called Qt Designer, where you can make layouts for what your UI needs to look like. Okay, here you have buttons, all this stuff you can drag in, and you make what your UI is going to look like. And here you can also associate functions to sliders. For example, if I move this slider, it will go and call a function call, which needs to be there in your Python instance, which we'll later come back to. Now, this is compiled to a python.ui file with a Python class representing this layout. And all that is done by PyUIC. There are several tutorials available for this. You can look it up. And once I have this, I can write the rest of the code, which will, of course, use that particular layout. And now, this raw data that you see, one second. This raw data can be analyzed with several of Python's functions. For example, if I want to know what the frequency of this data is, okay, this oscillating function, okay, one is that I know what frequency I set here, fine. But this extracted data, which is basically a time, on the x-axis you have time, and on the y-axis you have voltage. So from this, you can fit this using regression to a standard sine function, and you can extract the frequency here. So it says here that it's 2721 Hertz. And to make this a little more interactive real-world experience, instead of using the waveform generator, I'm going to use the microphone input. So here I'll enable the microphone input, and here, not sure you can see it clearly, there's a small microphone plugged in here. And what I'm going to do is I'm going to whistle and try to extract the frequency. So you see the frequency of my whistling was 2100 Hertz, and you could see the corresponding sine wave here, correct? So if I just up the pitch a little, so you can see that you can extract from the raw signal the amplitude as well as the frequency. Now I'm going to use the piezo buzzer again. I'm going to plug it in here, use the signal from that. Okay. Approach the resonant frequency so the signal is loud enough. So now you can see that the piezo buzzer is resonating and the microphone is picking it up, and you're able to view what the signal's frequency and the amplitude is. Another mathematical function that we students are taught from class 11th onwards is the Fourier transform. Now, we learn the equations, but we never actually see it in action. So here is a very easy way to see a Fourier transform in action, and what it essentially means. So I'm going to take a Fourier transform of this signal. So you see, the Fourier transform here is a single peak with a fundamental at 3200 Hertz, which is the frequency we set for this buzzer. Now, if I change this buzzer signal here, so 3300, take another Fourier transform. So you see, a Fourier transform extracts the fundamental sine component from it. Now, let's make this a little more interesting. We're going to take a secondary buzzer. Okay, so here I have a secondary buzzer. I'm going to plug it into another waveform generator. Let's say one here. That's SQ1. And I'm going to set this to 3500 Hertz. So does this pattern look familiar? This is your beats phenomenon, right? If I let me just freeze this here. Okay, so one buzzer is resonating at 3300. The other one is 3500 Hertz. So according to your textbook knowledge, 200 Hertz is the beat frequency. Can we verify that? So you have the time scale here. It's 4 milliseconds here and about 9 milliseconds here. So that's about 5 milliseconds for one beat, which corresponds to 200 Hertz, which makes sense. But here, you're not able to extract the frequency accurately because this fitting function relies only on one sine function. And this is where you can see the power of Fourier transforms. If you just take a Fourier transform of this signal, what you get is going to be the components. So you can clearly see here, you have one buzzer at 3300 Hertz, which we set here, and another at 3500. So your Fourier transform is able to extract and show you what all the component frequencies were. Now, if I mix in my whistling at, let's say, another frequency, let's something else, and we'll get a third peak. So watch. So you have buzzer 1, buzzer 2, and my whistling, which was at 2000 hertz, 2100 hertz or so. Now, yeah, so let me just come back to my slides here. I need to pause these two. Yeah. Okay, so I've introduced, some parts of the hardware now. And we saw how we could make UIs with Qt Designer, and I'll move on to some sample experiments. 3 experiments I've listed as which are sort of interesting. And yeah, so one here would be oscillations of a simple pendulum. This is a recording, I'm not showing it. What we have here is a DC motor. Now, a motor works both ways. You can either apply a voltage and you have a coil deflecting, which causes the motor to rotate, but the converse is also true. If you simply move the coil within a magnetic field, there's a voltage induced. Now, this induced voltage is proportional to the speed at which it rotates, right? The rate of change of flux. So what we have here is we have a pendulum attached to a DC motor. Now, as the pendulum oscillates, the voltage induced will also oscillate. And from that, you can extract the oscillation frequency of the pendulum and the damping coefficients, etc. Okay, so now there is, within a very low bill of materials, we have a microcontroller, some basic analog electronics for measuring voltages, etc. And we've provided a communication bus, which is used to talk to sensors, which you can purchase commercially for a few dollars. For example, this one here is an accelerometer plus an angular velocity sensor. It's a 6 degree of freedom unit, which is used in your phones for playing games. So when you tilt your phone, how does your phone know that it's been tilted? So this particular IC is there. Now, what we want to do is we want to get this data from this IC through the device to a Python your interface where you can visualize it and use it for educational purposes. So here you can see there's an oscillating pendulum with the sensor attached to the pivot, and the acceleration is here and angular velocity. Sorry, this is theta, and you have angular velocity here. So you can see at mean positions, you have maximum velocity, mean position, maximum velocity in the other direction. And at the extremes, you have 0 velocity. So there are several sensors like these, which you can purchase commercially. One that is plugged in here, I'm not sure you can see it clearly, but let me just see the video screen. It's barely visible. You have a very small sensor here plugged in to the communications port. And this is actually a LiDAR. And what it does is it sends light pulses, waits for the light pulse to be reflected from any surface nearby, and measures the time taken for light to travel from here and back to the sensor. And from that time and the known speed of light, it measures the distance. And this thing is, anyway, it sounds fancy, it sounds expensive, but it's not. So again, a few dollars, you can purchase it on the internet locally, etc. And I'll just show a brief demo of the sensor. Go back to the UI here. And we've written all the protocols in Python for handling various sensors. They all use the same communication bus, but they have different command sets for extracting data. So I'll just go to I2C modules, go to general purpose I2C sensors. You scan for connected sensors, and it says there's a VL53L0X time of flight sensor connected at this particular address. You can have multiple sensors on the same bus sharing. So you see, if I place my hand here, it's actually measuring in millimeter units the distance between the sensor and my hand. So if I move my hand up and down, you can see that there's an oscillation. Now, how does this help? For example, if you have a mass spring system where this is the mass and it's moving up and down, you want to know the frequency of oscillations. You can just go to the data logger, which uses PyQt graph again for plotting. You can see that there are oscillations. You just pause this data. Let's just assume this is a simple pendulum, mass spring system. You select a region of clean data and sign fit. This again uses the previously mentioned method for regression. A standard sine function is used, and you have extracted an amplitude of 25 units, frequency of 1.229 hertz, you can also have a damped sine fit, for which you need a damped oscillation. So let me just simulate that. So, okay, some sort of damping I've created here. And you say damped sine fit. So yeah, you have a frequency and you have a damping coefficient. So that way, all your raw data, which may be crude, with Python, you can make it, you can extract parameters which make it all, a lot more meaningful. And I'll show you one more demo here, which, so I have here a sensor which measures pressure. It also measures humidity, and it costs maybe 300, 400 rupees in that range, depending on where you buy it. So since all these sensors use 4 wires for supply, ground, and there's a clock line and a data line, we use connectors which have 4 lines, and just plug it into your hardware. Okay, second. I touched the cable a bit. I think I need to reconnect.
Are you going to show your? We can see your face and not your board.
You cannot see. Yeah, the sensor's in my hand, so I don't think you need to see the board at this point.
Okay, fine. Yeah, that's fine.
Is that fine? Yeah. Let me just just go to general purpose sensors. Yeah. So now you can see that the previously connected time of flight sensor is still there, but at the same time you have a new sensor introduced here. Just going to log that. So you can see it measures 3 parameters. So there's temperature, that's 990 millibars, which is Delhi's pressure, atmospheric pressure. There's the temperature at 22 degrees inside my house. And this is humidity. So humidity, if I just breathe in, you can see humidity spiking. Okay, so coming back to pressure, you can use this in physics experiments. For example, measuring the relationship between pressure and volume. You seal this thing inside a syringe, compress the syringe and see how much the pressure goes up, and you tally your P1, V1 is equal to P2, V2. Or you can seal this inside a complete closed chamber and heat the chamber and see what the relationship of pressure with temperature is. And basic thermodynamics experiments can be repeated with very affordable, simple sensors. One very common phenomenon, which we just hear in schools, we never observe, is that pressure, atmospheric pressure, drops as you go up into the hills. And that's something you can feel if you actually go up into the hills or on a plane when the pressure, cabin pressure drops sometimes. But since this thing is so sensitive, you can observe this thing here without actually having to go up even a flight of stairs. So if I raise the sensor's height, can you see the pressure dropping here? Now, if I lower it,
yeah, that's
it's going to climb. Okay, I'm just putting it on the floor. So that's how sensitive MEMS devices have become. Yeah, so that's that. It's something you don't actually observe physically with any instrument, but it is possible. It's there. Okay, where are we as far as the time is concerned?
You have 10 more minutes to go. So
I have 10 more minutes, so I need to rush this quickly.
5 minutes for Q&A, so yeah.
Yeah, so that's about sensors. You can have other plug-and-play devices, again, commercially available. The job of the hardware is to be able to interface with these commercially available devices, and Python simplifies the whole interfacing part. Right, so now we saw that piezo buzzer experiment, and I'm just going to foray into a quick advanced logger utility, which, okay, so what I want to do here is I want to characterize the resonant frequency of a piezo buzzer. So I have here the piezo buzzer. Let me just show you the buzzer here. So I have the buzzer connected here, and I want to measure the amplitude as a function of the frequency. So it's loudest at around 3000 hertz, like I said, but I want to characterize exactly how loud is it. So on the x-axis, I should have the waveform generator, so you can hear it, right? I'll characterize from about 1000 hertz to, let's say, 4000 hertz. That's my, that's my x-axis. And on the y-axis, what I need is the amplitude. So amplitude needs to be extracted from the oscilloscope. So I have the oscilloscope here. I pick out the microphone channel. So in the microphone channel, you can see that parameters are extracted here. This is all done by SciPy's fitting modules. I require the amplitude, so I'm just going to select the amplitude. Amplitude is going to go from 0 to maximum of 3, so I'll just set that there. I need a time interval of 50 milliseconds between each data point. A settling delay is required for the piezo to respond. Once you set a sine wave, the piezo starts resonating properly after a short interval. So I set a settling delay of 100 milliseconds, and I take 50 data points. I say log data. Okay, so one small mistake I made here. I'll just correct that 1 second. So choose Y parameter, cross-check frequency. Sometimes the fitting doesn't happen properly. So I need to cross-check frequency. And if the frequency does not match with the set frequency, I need to ignore that data point. So confirm again. So you see, it had a spike at around 3,800 hertz, and the resonant went beyond 4,000. So again, X should go all the way up to, let's say, 5,000 hertz. So you see, this is the resonant curve. It's loudest at 2 distinct points here. There's a plateau around 4,000, 3,800 to 4,000 hertz. And so you know where your piezo is loudest. Now, one very interesting thing which you can do is, instead of connecting this to a sine wave, if I connect it to a square wave, what would you expect? I'm just going to set it to a square wave. My x-axis should be SQ1 instead of sine. Again, going all the way to 5,000. Minimum from 1,000 or let's say 500. Take a few more data points. I think I made a mistake somewhere. Oh yeah, this should not be there. 1 second. Okay, so does this make any sense? With this pure sine wave, we had just one, a frequency response curve which looked something like this at 3,800 to 4,000 hertz. But when you apply the square wave, if this 3,800, you have the same shape somewhere here at around 1,200, and then again a smaller one at around 700. So where is that coming from? So since I'm out of time, I'll quickly go to the results. So with sine, you had one peak, and yeah, so this is sample data that we took. So you know that a square wave, if you take the Fourier series of it, is composed of sine waves. So what the mechanical oscillator does is it picks up a frequency closest with which it can resonate. So even though you're at your resonance may be at 1250 hertz, at 1/3 of that, you will find the same shape peak at 1/5, at 1/7, and so on and so forth. And if you log, instead of the amplitude, if you log the frequency, you can actually see which frequency, closest frequency, the buzzer will latch on to. It will not latch on to any random frequency. It will only latch on to whatever component frequencies are present in the square wave. Okay, so now we're out of time. I'll skip to packaging. As I described earlier, I use PyInstaller for Windows, which is fairly convenient. PyPy is also there. It's also with one script, you can quickly upload your package, and pip install can be done. And otherwise, you can make a deb file for Debian-based systems such as Ubuntu. Now we come to translations. So if you use Qt Designer, this is very easy to translate. You have Qt Linguist, where you can have people who will translate each phrase used in the UI. And with one click, you can switch between translations. And since Python Sphinx is being used to build the help files, which are written in .rst format, you have a PDF document here in English. You have a French translation contributed by Georges Cazeneuve. He also wrote all the code that goes into Sphinx for compiling all these documentations. And the UI can be translated. It has been translated into Malayalam, Kannada, Telugu, Hindi, someone's doing. This is a Malayalam translation by Amal. So I can show you the whole thing in action also. If you just go back to the oscilloscope, you can just go to choose language and select, okay, I want to use Malayalam. So it will quickly switch to Malayalam UI. Or if you want to use a French UI, it will switch to a French UI. And you can also have, using Qt Web Engine, you have help files, which again are translated into different languages, depending on what language you selected. This is all in French. And this, we're out of time. You can access remotely using Python Flask. You can have a backend server communicating with XPython, and you have API calls to remotely access things. This is something we presented at SciPy last year. It's a much more simpler example of how you can use Python to hardware real-world bridge. All you need is a microcontroller where you replace the bootloader with a specific one, which you can find. The source is here. And Python code can be used to quickly toggle pins and read data, etc. Again, this is an example of what it looks like on the C side of things and what it looks like on the Python side of things. And yeah, that brings us to the end of my talk. Thank you.
So thank you for an amazing demo once again. It's really awesome, always inspiring to see this. There are a few questions. I'll start from the back, and we'll have to be quick because we have like just a minute.
Yeah, sorry.
So can we replace this system with the actual oscilloscope or FFT analyzers? Physical instruments?
No, so this is not, it's not a dummy device. It's actual data that's being acquired in real time. What you saw is all live data. But the specs are fairly low end. Like, for example, it can read 2 million voltages per second, as opposed to an oscilloscope, benchtop oscilloscope, which may be able to do 100 million. But again, the prices are 10 times more as well.
So the basic question is it good enough to be able to do school experiments and things is the question.
Yes. It's built as per curriculum. And if you look at my screen here, you can have various experiments. For example, measuring of all your standard electronics 101 experiments, such as half-wave rectifiers, full-wave rectifiers, op-amps, and so on and so forth.
Okay.
So there are help files detailed, for example, how to make filtered half-wave rectifier and what sort of data you would get and what the new voltage here is, etc.
Okay, so we have one more question on the stage, which I request that you answer offline because we just ran out of time. So
sure, no problem.
So I think Mukund has asked if we can perform modulation experiments. If you can just answer that on the chat.
Yeah, you can perform modulation experiments.
Awesome. Okay, and there are more questions coming up because they've created quite a buzz. But we need to move on to the next talk.
Yeah, so should I just click leave here, right?
Yeah, you can. So yeah, we're going to set up the next talk.
Right. Thank
so
you.
All of this is not recorded, but yeah, you can